Okay, everyone. I'd like to welcome everyone to today's public talk from the School of Physical Sciences, featuring mathematician Bob Pelayo. Today's talk is going to be discussing data science, from data science to biocalculus, transforming undergraduate math curricula at every level. Our speaker, Professor Bob Pelayo, is a real expert in this area and has been, I think, a transformative force at UCI when it comes to educating folks in math. So I hope you have a great time hearing this talk today. I know I'm excited to see it. Let me give you a brief introduction here to Bob, and then we'll get started. So he was actually born and raised right here in Southern California, and he got his Ph.D. in mathematics from Caltech. He actually taught for 11 years at the University of Hawaii at Hilo, and then we were very fortunate to recruit him to come join us at UCI in 2019 as teaching faculty. And as I said, it's just been amazing to watch everything he's spearheaded and done since he's come. He's actually currently the vice chair for Undergraduate Studies, Curriculum and Planning for the Mathematics Department at UC Irvine. And as we're going to hear today, he's actually successfully obtained a number of very large grants to help rethink education in mathematics, including he's PI on a $1.4 million grant on BioCalculus, which is funded by the California Learning Lab. And you'll hear about a few others as well. He's had a lot of experience in creating high school curricula for College Board and the Hawaii State Department of Education. And he previously founded the data science program at the University of Hawaii at Hilo when he was there. And he's currently working on doing a number of exciting activities here at UCI for us now. And so before I hand it over to Bob, let me just say there is a Q&A box that you should have access to there. And if you have any questions throughout the talk, please go ahead and just type those into the Q&A box. And I'll be fielding those questions and then asking Bob in real time. And there'll be a few clear times that you'll see you'll be able to ask questions throughout the talk. Okay, and with that, Bob, I'll hand it on to you and you can go ahead and share screen. Thanks a lot.
Okay, get the share screen right, first of all. Okay, thank you, James, for that great introduction. Back when I was in college, I used to have this fun question that I would ask my friends. What do you think that I study all day as a mathematics majors? And the answers, they always made me smile. You do things like multiply a whole bunch of big numbers in your head, like I was some kind of a math magician or something. Or you solve really, really long and complicated equations. In fact, one of them told me that you always look mad when you're doing mathematics. You think for a long, long time, then all of a sudden you excitedly scribble down a whole bunch of nonsense on your paper. Well, now that I teach mathematics, I still ask my friends exactly the same question. What do you think that math professors do all day? Well, they say, now you actually teach students how to multiply those big numbers in their head and how to solve those complicated equations, as if calculators and computers don't exist or something. And that I still scribble nonsense, but this time on a whiteboard instead of on a notepad. So all of these interactions have led me to conclude that the inner workings of college-level mathematics courses are usually not front of mind for most people. The belief is that math majors just start off studying a whole bunch of calculus, and then for the remaining 4 years, they just continue to do more and more harder and complicated calculus. It is unclear to most that there is actually a rich diversity of mathematics courses and pathways. And it is even more unclear that there is quite a lot of potential to innovate and to transform how we teach these important courses. So what does happen in a typical math major. Most college students enter and leave math as part of our lower division courses on the bottom of that chart. These are mostly service courses that frequently serve as prerequisites for other majors, where students obtain quantitative and computational skills that are required for their later work. Math majors, though, many of whom have chosen mathematics because they are good at calculus and at the more computational courses, then need to change the way that they think about mathematics. They transition from users of mathematics to creators of mathematics. This requires speaking and writing in a completely different language, the language that includes abstraction and proofwriting, which is taught as part of our transition courses. The upper division courses, that's where our math majors have the ability to both abstract and to specialize and concentrate. Upper division courses search for deeper structures in the mathematics taught at the lower levels. In these courses, students have the ability to hone their skill sets towards specific career ambitions. Pure math majors, for example, search for mathematical abstraction, while financial math majors study concepts like modern portfolio theory and develop financial models. Applied math majors, on the other hand, use computational tools to find or approximate solutions to questions that are posed in other scientific fields. Then there is my favorite, which is data science, that brings together mathematical modeling, statistical thinking, and computer science tools to analyze complicated data sets in new and efficient ways. So what specific courses do these students take at the different three levels? Well, the lower division courses, they are some of the more familiar ones. For example, calculus, which is depicted here in the bottom and middle, studies change and accumulation and is utilized by almost every single STEM major. Linear algebra, that is depicted to its right, introduces the study of matrices and is often taken by engineering students. These courses are marked by their reliance on computational procedure. Students want to know how to solve a specific problem. Contrast that with our upper division courses, where this perspective changes, where now math majors ask questions like, why does something work? And how can we generalize lower division ideas to help us to understand more complicated models? Pure math courses have names that sound simple and straightforward, like, for example, algebra and analysis, but these are usually some of the most difficult courses that we have. We also take a lot of the various ideas from computational math, like, for example, derivatives and matrices, and generalize them to form powerful tools, like, for example, neural networks that you see on the top right-hand corner. In the middle, though, there is this awkward transition that is in between the computation at the lower level and the abstraction at the upper level. This is the adolescence of mathematics, where our students start to identify as math majors and start to speak that language of mathematics. This requires a huge paradigm shift for both students and also for instructors. So there are clearly a lot of opportunities to improve and to transform math education at all three of these levels. This presentation is the story of what happens when, during a pandemic, you apply for 3 large grants, hoping that you'll maybe get just one of them, and the amazing opportunity that comes when all 3 of them are actually funded, and you can strengthen the entire mathematics pipeline all at once. We will start with lower division courses by introducing the $1.4 million BioCalc PEA Project, which helps to transform the curricula for our popular BioCalculus course. Then we will focus on transition courses by describing the $300,000 Noticing in Mathematics for Student Success Grant, which adapts the pedagogical technique of teacher noticing to our Intro to Abstract Mathematics course. We then end our by discussing the upper division concentration and course pathways by highlighting the $1.5 million Southern California Data Science Fellowship that provides internships and other training opportunities for our data science students. We begin with thinking about our computational courses. Calculus, of course, is the first that comes to mind, but many of our lower division students actually take content-specific calculus courses, like, for example, the BioCalculus course, Math 5A and Math 5B. These courses are almost exclusively populated by biosci majors, most of whom have pre-med ambitions. This class, though, is a bit of a rarity. It is not a prerequisite for any biology course, and it is often taken in the second year and sometimes as late as the senior year. So how do we craft a BioCalculus course where the calculus might not actually be used for any biology? This brings us to the BioCalculus problem, which highlights why BioCalculus seems so detached from the biology major pathway. On the left is the table of contents for one of the most popular calculus textbooks on the market, Calculus by Stewart. This is what I used to learn calculus back in the day. It is a solid calculus textbook that is used as part of our traditional calculus course sequence, which is called Math 2. The chapter titles may be familiar to many of you. For example, functions, limits, derivatives, differentiation rules, applications of these derivatives, and then integrals, and then more applications after that. Fond memories, all really, really good stuff. However, something interesting starts to happen when you compare it to the BioCalculus table of contents that is pictured on the right-hand side. On that right table of contents, we see that it is almost identical to that of the traditional calculus course. Once again, we see functions and limits and derivatives and applications and integrals and more applications. This similarity is not just true at the chapter level title. Many of the computational examples inside of the actual textbook are the same, with many of the homework problems completely identical. In other words, BioCalculus is really just regular calculus that is dressed up as biology. This means that our BioCalculus students leave our course wondering why they can't just take that traditional calculus course sequence. The kind of mathematical thinking that is used in their biology courses is absent from that BioCalculus textbook. Therefore, many of our students think that the BioCalculus course is a potential barrier to their success that might lower their GPAs, instead of actually being a useful tool that will further their careers. This BioCalculus problem was the impetus for the BioCalc PEA program. This is a $1.4 million grant from the California Learning Lab, for which I serve as principal investigator. Our team of a combination of math and biology faculty from 3 campuses, UCI, CSU Fullerton, and also Fresno State, saw that same disconnect in each of our schools and recognized an opportunity to offer students a curriculum that more fully integrates calculus skills into the biology course pathway. The PEA actually stands for something. The P is for preparation, where we will host summer academies and modify first-year experiences to introduce biology students to mathematical models and what is called proto-calculus. The E is for engagement, where we redesign our BioCalculus course curriculum to be motivated by biological models instead of by traditional calculus concepts. This new curricular package will also include active learning that is embedded in teacher-facing and student-facing material that will be available for free as an open educational resource. The A stands for application, which is where we include calculus concepts in upper division biology courses in a careful way to ensure that students actually see calculus beyond their mathematics courses. So this reorganization of the BioCalculus course flow is a major one. On the left-hand side is that BioCalculus table of contents that we previously saw, organized by calculus concepts. On the right-hand side, though, that is the proposed chapter structure for the BioCalc PEA course package that we are currently developing. Notice that it focuses on function models. Why? Because biologists think in terms of which functions are the most appropriate to model their particular situation. They don't think about chain rule and antiderivatives and related rates. Rather, they wonder if a population grows exponentially or logistically. To be clear, the BioCalc PEA curriculum is still a calculus curriculum, but the math concepts and the calculus concepts, they are strategically spread out throughout the various models. For example, we use chapter 1, which is called linear functions, to establish the concept of constant rate of change. Then in the next chapter, quadratic and polynomial models, we introduce the average rate of change and then the instantaneous rate of change. What is called, of course, the derivative. And instead of just blowing through a whole bunch of differentiation techniques, we stick to the ones that are most relevant for that particular function model. So where do we introduce things like quotient rule and product rule and chain rule? They fit more naturally in chapters like rational models and the exponential models, respectively. Each chapter will start off with a video from a biology professor that is posing a biology question that requires calculus to give a biology answer to it. Thus, the calculus is a tool in service of biology. The need for concepts like limits and optimization and related rates come from carefully chosen biology question. It is a course that focuses on biology first. Since this is the first grant that we will discuss, I wanted to provide an opportunity to field questions on the $1.4 million BioCalc PEA project.
Thanks so much, Bob. We already have one question, so let me ask it, and then I'll invite others if you can think of questions. Go ahead and do that. So you talked a little bit about these summer academies. Can you describe those a little bit in a little bit more detail?
Sure. So the summer academies, they will be hosted at UCI and also at CSU Fullerton. They will be 2 to 3 week summer experiences that will bring rising freshmen that are biosci majors and essentially run them through the connection in between biology and what is called proto-calculus. So proto-calculus is essentially towards calculus. We don't want to use the word pre-calculus just because that's sort of a weighted word, but we start to slowly introduce them to things like the derivative, not the formal one, but just towards it. and similarly with integration. So these will be about like 20 to 25 students in that first year. The one at UCI will actually start in September, and the one at CSU Fullerton start in August. And it is really an opportunity for students to, at the very beginning, start to see that connection in between the biology and also mathematics.
How do you choose the students that are able to be involved with these summer opportunities?
Right, so we are trying to target the students for which that extra experience might be as beneficial as possible. So we have a lot of students that will certainly benefit from about 2 to 3 weeks of mathematical review and positioning. So then we're going to work with the biology departments and also admissions to try to select those kinds of students.
Yeah, fantastic. Thanks. So a couple questions. Will the result of this grant be a new textbook? And if so, is the book available now? People are excited about this potential for a book.
Right. So we actually want to break away from that mold of a textbook. I think that that's been the concern with previous BioCalculus delivery. The BioCalculus textbook, it is certainly perfectly fine, but it does not give opportunities for the instructor to actually engage students. So instead, we call it what is called a curricular package, where it does include quite a lot of student-facing material, but it also includes things like lesson plans, in-class activities, project ideas, homework problems that will be free, that are fielded in the platform that's called My Open Math, which is one of these freely available resources. So in the future, in about like a year and a half or so, we do expect to be able to disseminate the curricular package, not the textbook, but the whole curricular package to whoever might benefit from it.
Oh, wow, that's great. And then, and this will be widely available. It'll just be,
yes,
you'll put it on the web and anybody
yes,
can grab it.
Absolutely.
Great.
Absolutely.
And are there another question is, are there other universities that are also exploring new models for BioCalc or
Oh, sure.
sort of look into and get ideas from?
Yeah, so I've been contacted actually by probably about like 3 or 4 schools that are from the UC system and also the CSU system that are trying to figure out how to appropriately teach biocalculus. They have exactly the same concerns, that it is essentially a calculus course with a few biology examples that are thrown in there. Now, they're really good biology examples, but when they give exams, for example, it really feels like a traditional calculus exam. So we are trying to see how to strategically partner with these other schools at the UC system and also the CSU system to be able to make a product that is as effective as possible.
That's fantastic. So another quick question. Is this, just to clarify, this is aimed at pure bio and not, say, bioengineering students?
Yeah, correct. Well, so we actually choose the biology applications and motivations so that they actually come from a very rich field of biology. So things like ecology, but also biochemistry, anatomy and physiology. There's going to be quite a lot of very different biology concepts that are represented there.
And then I think we have one last question on the Q&A. And just to remind everyone, if you have a question, the best way to do that is just use the Q&A box and type it in there. That's really the only way we can hear from you. And then, so we currently teach a class, Math 1B, which is kind of a pre-calc class.
Yes.
Is there overlap there, or are you thinking, is this summer program instead of that? I mean, how does that work just in the context of like the general curriculum we teach along with 1B?
Right. So the Summer Academy, it is really to connect biology concepts to before calculus mathematics. I don't want to use the word pre-calculus, but really before calculus, so that students can actually start off their university careers knowing that mathematics is actually a huge part of what they're going to study as part of their bio majors. So because of that strong focus on biology, it's actually pretty separate from courses like Math 1B.
Great. Thank you. And then I guess we have one last question here. Have you included any practical integration with CSU Fullerton, such as with Dr. Joaquin Schenk in the plant H2O lab? I don't know that lab, but are you familiar with that?
We are instead working with one biologist that does fish biology, and we have two professors in the CSU Fullerton mathematics department, the chair of math and also the main instructor for their BioCalculus course. So not that particular professor, but we do have representation from the Fullerton biology department though.
Great. Thanks, Bob. All right, I think we're good, and we'll let you proceed with the next step of your talk.
Okay, thank you. Thank you. Now we move up a level to our transition courses, where there's quite a lot of work to be done in terms of bridging the computational courses at the lower division to abstract mathematics at the upper division. Our critical transition course is called Math 13, Intro to Abstract Mathematics. It is required for all math majors and is a prerequisite for almost all of the upper division math courses. However, it is really difficult to teach this course, and unfortunately, our students struggle. Many times, there are several per year that actually switch out of mathematics because of this barrier course. So what makes this course so difficult to teach? Well, we are asking students to change the level at which they engage in mathematics. Think about, for example, the concept of the limit, a foundational idea from calculus. On the left-hand side, we see a typical lower division calculus problem where a student is asked to compute the limit of a function. Now, students slowly get the hang of this. For example, here, they are asked to compute the limit as x goes to -3 for our function that is presented graphically. So what do students do? They start to visually plug in x values that get closer and closer to -3, and they see that the height of the graph of the function starts to get closer and closer to 4. So there's your answer, 4. Math majors, though, start to realize that words like closer and closer to are probably not precise enough. So as part of the upper division courses, like for example, elementary analysis, we ask students to formalize their mathematical thinking, to provide precise definitions for concepts that they used to just wave their hands to. On the right is the actual formal definition for the limit, exactly that thing that we computed on the left-hand side. Bear with me as I read it so that we can all appreciate the huge cognitive jump that we ask our math majors to partake in as they transition from lower division mathematics to upper division mathematics. We say that the limit as x goes to c of the f of x is equal to L if for all epsilon greater than 0, there exists a delta greater than 0, such that whenever 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Whew, that was a lot. Here, close to, that is replaced by things like absolute values and epsilons and deltas. This is hard for everyone, including math majors. In fact, it requires a new way of describing mathematics, one that is taught in important courses like Intro to Abstract Math. What else do we do in this critical course? We generalize math concepts. For example, on the left-hand side, we have a function where you plug in some kind of a real number, do some kind of an algebraic compilation, and out comes yet another real number. On the right-hand side, though, those are the kinds of functions that we try to abstract to in our upper division courses, where, for example, instead of plugging in and getting out numbers, you can instead plug in a shape and get out some kind of a color. So we generalize the concept of function by generalizing input and output spaces as well. We also make conjectures. On the left-hand side, we are asked to add up the first few odd numbers and see a pattern start to emerge. Work with me. So 1, of course, is equal to 1, and 1 plus 3 is equal to 4. 1 plus 3 plus 5 is equal to 9. 1 plus 3 plus 5 plus 7 is equal to 16. And then the bottom sum is going to give us 25. So, of course, if we think about what that sum looks like, 1, 4, 9, and 16, and 25, we can identify that it's probably going to be perfect squares each time. But will this always be true, or is it just true for those first 5 examples? And if it is always true, how do we actually prove that that pattern will always hold? We also like to formalize definitions. Let's think about something as straightforward as fractions. Most of us recognize that the fraction 18 over 12 is the same as the fraction 3 over 2. But why? What does it mean for 2 fractions to be the same? And in fact, what even is a fraction? Mathematicians formalize everything, including fractions. We see fractions, or rational numbers as we call them, as pairs of numbers where 2 pairs are equivalent if a certain algebraic condition is satisfied. This formalizing for even really basic ideas like fractions is hard, but it is really necessary. And it is the cornerstone of all mathematical progress. Now, the hardest part of abstract mathematics, that is actually proving a mathematical statement. It is not hard for most people to convince themselves that some kind of a statement is actually true. For example, consider that statement that we see in the middle of our screen. The sum of any 3 consecutive whole numbers is divisible by 3. Let's try to convince ourselves. We can start off kind of easy. 1 plus 2 plus 3, that's going to be a 6, divisible by 3. Let's ramp it up a little bit. 5 plus 6 plus 7, that'll give us an 18. 6 plus 7 plus 8, that'll give us a 21. All of those being divisible by 3. It seems like it's always true. And in fact, some of us may even start to see why it is always true. So how do we formally prove something? We write what is called a mathematical proof. What is hard for so many students is that a mathematical proof is actually mathematical prose. It is a paragraph, or sometimes many paragraphs, containing mathematical argumentation. For example, towards the bottom of the screen, you can see a short example of a mathematical proof. Yes, it has some computation inside of it, but it also has nouns and verbs and periods and commas. But this is the lifeblood of mathematics, the mathematical proof. It is how we are certain that mathematical statements are always true. In our abstract math class, we ask students to write these pretty complicated proofs when only a year before that, they were happy computing derivatives and antiderivatives. This means that quite a lot needs to happen in a single quarter. Thus, investing in these important transition courses is very important. This is where we turn to teacher noticing. We partnered with the UCI School of Education to obtain a grant from the National Science Foundation that is entitled Noticing in Mathematics for Student Success for $300,000, for which I serve as one of the co-PIs. This grant will use teacher noticing as part of the Intro to Abstract Math course. Now, teacher noticing, that is a pedagogical technique where teachers are trained to listen to and to respond to student thinking. Here, both the correct and the incorrect answers are lauded. We are less interested in the correct answer and more in the thought process that goes behind getting to that correct answer. This technique has proven highly effective in many academic areas, but almost exclusively at the K-12 level. What makes this project so innovative is that it is one of the first times the teacher noticing is being adapted to higher education mathematics. As part of this grant, we will develop video recordings of students that are sharing their thinking as they work through the proofwriting process. These videos will be collected and annotated to help to train entire instructional teams on how to respond to and encourage student thinking. Thus, this training includes more than just the instructor. We will also train the graduate student teaching assistant and also the undergraduate learning assistant. So this is a novel use of the technique that is called teacher noticing. And we will also study the efficacy for teacher noticing as part of higher educational mathematics and measure the potential to which it can be used in more college level mathematics courses. So similar to before, I'd like to pause for questioning on the second grant, the $300,000 Noticing in Math for Student Success.
Thanks, Bob. So we've got a couple questions already, one of which was just asking if we were going to post a video of this talk, and the answer is yes. If you go to the School of Physical Sciences homepage and look through the events tab, you will find a link to all of our virtual talks that we've done in the last several years. And this will be up there, I hope, within a day or so. There's also, the School of Physical Sciences has a YouTube channel. So you could probably just find us on YouTube as well, and you'll find a lot of our talks there. So thanks for that question. A couple of other questions. So how do you convince students that things are all, that if you have something that's kind of already clear, that then this needs a precise definition?
Yeah, so this is probably one of the hardest parts of teaching a course like this. That even like basic algebraic procedures, like when you divide by 3 on both sides of an equation, all of this needs to be justified. And a part of what we do in that course is that we need to set a baseline for the basic kinds of things that you can assume mathematically and where they come from. So probably one of the hardest parts is going to be to introduce students to what are called the axioms of mathematics. Like these are sort of like the basic rules. So all definitions and all concepts, they need to be described in terms of those axioms and their consequences. Now, this is hard. It usually takes a couple of courses to actually get this correct. But one pretty common technique is to try to use like these so-called like sloppier definitions, like quasi definitions, and try to actually write down a proof with it. And because it's not completely formalized, that proof doesn't exactly flow, doesn't exactly make sense. So this pretty quickly convinces students that more formal definitions are actually required. That's not to say, by the way, that that using these previous concepts is a bad idea. In fact, part of the teacher noticing that we're going to be doing is that we will ask our students to actually use their previous knowledge about things like fractions to motivate some kind of a response, then to see that cognitive change when they actually switch from the more quasi definition to the actual formal definition, and try to make those connections, record those connections, use those connections to actually train future instructional teams.
Wow. Well, thanks. Another question. You mentioned this teacher noticing, and it was relatively new in higher ed math. Where else has it been used in college level classes that you're aware of?
Yeah, so actually not that many places. There's a small handful of studies in the biology setting, and maybe about 1 or 2 in mathematics, but 99% of the studies, they've been at the K-12 level. So not just in higher ed mathematics, but just like higher ed in general, teacher noticing that is relatively new. So then therefore really has a big potential to it.
Great. Well, I think that's good for now. So why don't we, I don't want to run out of time. So why don't we let you proceed, Bob, on to the next section.
Thank you, James. Lastly, we turn our focus to the upper division courses and tracks where students can specialize and concentrate on these in-demand skill sets. The newest and most popular math concentration is called data science, which has about 80 active upper division math majors each year. Data science concentration offers great courses, like, for example, optimization and numerical analysis, and it requires one not in math upper division course. However, at the end, our students graduate with a bachelor's of science in mathematics, where it is not clear on their transcript that they actually concentrated in data science. As a math program, we currently don't have any kind of a project requirement or an internship requirement, which may limit our students' marketability. Part of the challenge with crafting a data science curricular pathway is that it is not even clear what is data science. Data science it is something that is proudly interdisciplinary, but what are those necessary disciplines? Try to Google data science Venn diagram, and you essentially get every single possible combination of data science buzzword that is out there. Sometimes data science that is called the intersection of things like mathematics and computer science and stats, or sometimes it is domain expertise, and sometimes it includes things like data consulting and the scientific method, and sometimes it's not even the intersection of all of those, but the union of all of them instead, the collection of all of them. Like the diagram that is on the bottom right hand corner, sometimes these Venn diagrams are more complicated than they are helpful. So how do we craft a marketable data science curriculum if we don't even agree on what data science actually is? So because of this, where data science lives in the academic ecosystem is an interesting question. Even within the UC system, various different models emerge. For example, some schools create their own standalone divisions and institutes, and some position them inside of existing academic units. Even within UCI, we see the diversity of data science offerings. There is, of course, that math concentration in data science, but there is also a completely separate Bachelor's of Science in Data Science that is within the stats department. So not a part of the School of Physical Sciences, completely different school. In fact, it is uncommon to have a data science program that is positioned inside of a math major. Instead, they are usually parts of programs like stats or computer science or engineering. So therefore, what are the upsides of having a data science program inside of mathematics? Well, students will leave with a very solid theoretical background on data science topics and techniques. And because of this, many of our students easily transition to graduate programs that are related to data science in academia. There are, of course, quite a lot of limitations, mostly workforce limitations. Our students don't have that broader programming experience that a data scientist that is part of a stats or CS program would have instead. And our students often have difficulty marketing themselves to future employers, since on paper, they are really just seen as just a math major. They also lack robust portfolios of projects to help them to showcase their skill sets. So to help to improve and coordinate our data science curricula, a team of faculty from UC Irvine and CSU Fullerton and Cypress College have obtained $1.5 million from the National Science Foundation to run a grant that is called the Southern California Data Science Fellowship. I serve as one of the co-PIs that is on this grant. And across all three campuses, this grant will fund the creation of new data science courses, including courses like the Intro to Data Science, Bayesian Stats, and a project-based machine learning course. For several UCI undergraduate scholars, we will provide data science boot camps and stipends, and we will also pay these students to experience summer research in cooperation with a few industry and also academic partners. This summer experience will culminate with a research symposium where our data science fellows will demonstrate their skills in communicating with stakeholders. Thus, these students will leave our program with a robust portfolio, programming skills, and real-world experience that will help them to more seamlessly transition to the data science workforce. And for this last grant, I'd like to once again pause and field questions on the $1.5 million Southern California Data Science Fellowship.
Hey, Bob, thank you. Sorry for that technical difficulty. So here's a question. What are some of the industry partners supplying research questions for this fellows program?
So there's actually a couple of county agencies from Orange County that are interested in partnering with us. And as well, the Children's Hospital of Orange County and the Lawrence Livermore Grant, the National Lab.
Thanks, Bob. That's so exciting. I have to say that you have these partners, and there's such an urgent need, I think, at every step of the way that you're describing. We were talking a little bit earlier, actually, before folks joined, about the state of kind of math curricula in general.
Yes.
And what are your thoughts on that? I mean, is it that math education is just in trouble and we need to sort of change it? Are we adapting to the times? Is this a workforce question? I mean, what's the context of where we were with math education and where we're going?
When I talk to a lot of people, they always ask me the question, what more is there to do in mathematics education? Like, for example, calculus, which is essentially what most people think that mathematics education is all about. That's been around for like 300 or 400 years. So it is not clear to most people why there is even space to be able to really change or to modify. So most of the aspects of math curricula that need transformation, they actually stem from changing workforce expectations. Like, for example, more requirements of things like programming skills. That's actually hard to embed as part of a mathematics program because we don't usually include a lot of programming in our classes. Now, slowly that is changing, and the students are really starting to expect that they will leave the math program with enough programming experience to be able to easily transition to some kind of a job. The other big change, though, that is all of the advances in terms of just how we learn mathematics. That old school model, I think, that's called the sage on the stage, where you have smart professor that is standing at the chalkboard or whiteboard, essentially just like giving a whole bunch of information, that has been shown to really not be very effective. There is an increased reliance on things like active learning, more fully engaging the student learner as part of the experience. So really those two things, new techniques in terms of pedagogical delivery, and also changing workforce needs that are really requiring a lot of updates to the math curriculum.
Thanks. Another question for you. What is it from your personal experience that inspires you to bridge these gaps in mathematical education? Is it something from your experience, or is it just a general concern, or what inspires you to do this?
Right. So I've been in the math education field for maybe about 20 years now. And it is really reconnecting with students that have gone through my mathematics program and seeing that some of them really still struggle a bit. So trying to listen, what are the skills that would have made it easier for you to get to that grad school, to be able to get that research experience, to be able to get that data science job. That's really what I've been responding to. And pretty interestingly, those concerns have actually changed. About 20 years ago, there was really more of a focus on things like trying to get into grad school. But probably in the last 5 or 10 years, it has been about trying to get these data science jobs and seeing that our students really, really struggle because when they go for job interviews, what they show is essentially their transcript, where it's not really clear that they have firm data science skill sets. So then instead trying to, for example, give them these research opportunities and these internship opportunities, that is a very important line item that they can put on their CVs and their resumes. So it really has been responding to former students and a lot of their concerns and their suggestions. That has fueled me.
Great, thanks, Bob. So I guess we have time maybe for one more question, and this one is, I'll just read it. How can you apply abstract math concepts to new variable derivation operations during data wrangling to work in data science projects? So I guess it's sort of relating abstract math concepts to data science.
Right, so this is actually like part of a broader question that really highlights a very interesting observation. A lot of the people that do data science research now, they actually started off more as pure mathematicians. And that transition from studying things like linear algebra, vector spaces, and gradients and stuff like that, they are actually not finding it that hard to transition to data science. A lot of the people that actually teach our data science courses inside of the mathematics department, they have pure math backgrounds. I think that probably the main advantage here is that you already know about the basic structures and the tools of things like matrices and gradient descent and stuff like that. So just marrying those abstract concepts with things like computational tools, that's not a hard jump for a lot of pure mathematicians. It really just requires like learning a bit more coding and really just like a little bit of patience. But that does require some training and really learning new languages, like for example, R and Python or SQL as well too. So quite a lot of opportunities for pure mathematicians to actually transition to data science.
Fantastic. Well, Bob, thanks so much for this great talk. So inspiring. And
thank you, James.
Let me just, for the audience really quickly, we've got a bunch of really other interesting talks coming up. We've got a compelling conversation on diversity, equity, and inclusion in physical sciences on March 3rd. We've got I'm going to be doing what's called a fireside chat, our first one about quantum science research on March 30th. On April 5th, we have a virtual Rhinus lecture from Donna Strickland, who won the Nobel Prize in Physics in 2013. We've got a live event from the Newport Pier on April 22nd, which is work around the oil spill and what that's doing to the content of the oceans there. We have a Celebrate Physical Sciences Alumni Hall of Fame event on April 23rd. And finally, on May 25th, we have our chemistry alumnus, David McMillan, who just won the Nobel Prize in Chemistry. He will be giving a special talk at the Barclay Theater that will be a real live talk with a Nobel Prize winner, the most recent one from UC Irvine. So letting you all know about that. And again, I, for one, am so proud that we have folks like Bob here in our school, really at the cutting edge of math education. And as we all know, math education is so important these days. And it's just a pleasure to have you here, Bob. So thanks again, and I look forward to seeing you soon.
Thank you, everyone.
Yeah. Bye, everybody.